Yeah, great. Thank you very much for the kind invitation. Thank you for giving me the opportunity to be here. Today, I'm going to talk about building autonomous vehicles with almost no labels. Yeah, my background is that I worked for 4 years in a robotaxi company called Motional, and the last 2 years I've been at TU Delft as one of the previous speakers here as well. And our group in TU Delft is called the Intelligent Vehicles Group. We try to cover all things related to autonomous driving, from perception, that's also my focus, to dynamics control, human factors, etc., and also to some extent planning. And yeah, we really try to cover the whole AV stack. We have a nice prototype vehicle that you've already maybe seen on some of the previous videos here, and also a nice simulator. And if you have not heard of TU Delft before, so TU Delft is a technical university in the Netherlands, close to Rotterdam, with a nice campus. And if you're looking for an excuse to visit us, it was already mentioned, there will be RSS in July in Delft. And we will actually be giving a little demo there for advanced vehicle summoning. So a little bit like what you can do with your Tesla, but in our case, in the presence of vulnerable road users. So lots of brave PhD students will try to cross the road, and we will navigate around them and also crash test dummies, of course. Okay, let's jump right in then. So autonomous vehicle perception systems are trained, or also other parts of autonomous vehicles are trained with millions of examples. So humans annotate every single object that you have in those data sets. And if we change the conditions of these data sets and how they were collected, for example, if we go to a new city, or if we have a different sensor setup, maybe we get the latest LiDAR sensor also, or also if we have unexpected weather, then we need to start over. So then we collect more data, and then we just create a new data set, label that again with humans. And that's a lot of work, and of course also very expensive, and it simply does not scale. So maybe the weather conditions is feasible, but if you think of the cities, if you're just covering all of the US alone is already way more than any of the large companies can afford. So the question is really, how can we scale that to work in many cities and hopefully also in many countries eventually? And as I already mentioned, most of these data sets are annotated by humans, so especially when it comes to perception and 3D bounding boxes of high quality. Another aspect is also that it's often done under bad working conditions. So a number of media outlets have reported about that. Bad working conditions in outsourced labor, you can imagine that. So our goal is basically, how can we avoid or at least reduce the amount of human annotations that are needed for autonomous driving datasets and also datasets in other areas. And now I want to take a little bit of a look back at the past and the present and hopefully the future on the different types of datasets that we have. And I want to start with I call it generation 1, manually labeled datasets. So classic machine learning data loop is essentially we collect some data, we manually label it, we train a model, and then we deploy it. And this is basically fully supervised learning paradigm, which of course requires a lot of human labeling. And we did this in this nuScenes dataset that we created in 2018. Here's an example from driving in Singapore. So in this dataset, we annotated something like 1.4 million 3D bounding boxes by hand. Of course, not our own team, but outsourced again. And there was a lot of work, as you can imagine. And this data set is commonly used for perception. It's about 5.5 hours. It was very nice in terms of diversity, also in terms of the sensor setup used there. But of course, 5.5 hours is not a whole lot. And the question is really, how can we scale that up more? If we go on, yeah, this is another data set that you already saw in Javier's presentation to some extent. This is a data set collected at the university in Delft. So it's a little bit smaller in scale, but it's very nice in terms of the area, in terms of the challenges you encounter. So you can imagine this medieval environment, old town environment in the Netherlands, lots of canals, lots of challenges like that. And also lots of vulnerable road users. Again, here you see the cyclists crossing this bridge. So things that you would find to lesser extent in Arizona, Phoenix, or places, Las Vegas, some of these places where the big American robotaxi companies are tested. And this data set is also interesting because it was the first data set with 4D radar. So it's a new type of radar that also measures elevation, which is also interesting for other reasons. And then if we look a bit at data sets released up until nuScenes and also since then, the interesting thing is they're all kind of similar size. So the Waymo open data set is another one that's very popular. It's basically the same size as nuScenes, although they keep releasing kind of smaller updates for that. So the question is, in the end, why don't we have any bigger data sets? And I think the answer is probably doesn't make economic sense to go 10 times bigger than that and label that by hand. That just is not logical or economical. Another question is, are we still making progress? So this is from the detection challenge of nuScenes. So the goal is here to detect objects in 3D. The metric is NDS. It's a little bit similar to MAP, but you don't need to know all the details. We're kind of just listing all of the methods from the leaderboard. And what's interesting is that in the beginning, there was a huge improvement here, which is now somewhat saturating towards the end in the last year or so. And of course, you see all the different trends that we saw in general, fusion methods, transformers, etc. And another interesting thing is if you look at the colors, you see the different modalities. So for example, if we compare LiDAR only and camera only, in the beginning, so Tesla is famous for not using LiDAR and also radar ultrasound these days, just using camera, whereas other companies try to use as many sensors as possible and be redundant. And in the beginning, that was a very bad idea, I would say, at least in terms of the results that we have on this public benchmark. But nowadays, it is actually getting relatively close. So that is quite interesting, at least on this type of data, that camera only is getting more and more competitive. So conclusions, narrowing LiDAR camera gap, and also performance is somewhat saturating on this benchmark. So to summarize the first part, generation 1 datasets are manually labeled datasets. They kickstarted this whole data-driven perception era in autonomous driving. But of course, manual labeling does not scale. Performance is converging on the current datasets. We also saw that in the past with other datasets like Kitty. And obviously, 5 to 10 hours of data are insufficient to really cover all of the corner cases that you find out there in the world. So if you encounter an elephant on the road or so, then you have not seen that in any of these datasets. That brings me to the next generation of datasets, which I call generation 2, auto-labeled datasets. So now we have a machine labeling the data for us. The way this typically works is, again, we collect some data, we manually label it, we train a model from that, but now we have a nice model, nice perception model that can label our data. So now we can go in our loop, we can collect data, we can automatically label it with our model and train new models so that. And of course, we can keep on looping, finding more examples that are challenging and step by step getting to better performance. Here's a study done by Lyft together with their own data set. And the question was here basically, how much data do you need to develop a planner? And you see on the y-axis the number of interventions per 1,000 miles. So the idea is if an action was not safe, then a human would take over. And on the x-axis, you see the training set size. And what I mentioned before, nuScenes was around 5 hours of data. If you go from this amount to what they had in their data set, 1,000 hours, it's, well, let's say roughly 20 times less near collisions than in with the nuScenes amount of data. So it's clear that we need much bigger data sets. And it's also interesting that in their study, their data is collected from a single route, 6.8 miles long, 3 turns only, that leads from their office to the train station, I believe. So this is a very simple environment, 3 turns. It definitely does not generalize to level 5, and that's a challenge. Looking at some of the other data sets out there, so basically, we did a literature review and we found there was a common road benchmark that's from TOOM. It's quite interesting, kind of closed loop simulator, but it's relatively small. So it's mostly kind of handcrafted scenarios that you can use. It does not really have this large scale that we typically want for deep learning based approaches, but it is focused at planning. And then we look at all these various company data sets, Argo, Lyft, Waymo, etc. They are for prediction. So prediction means we look at the other agents, how they behave, not our own behavior. And they are getting bigger and bigger. So we have 300 hours, 1,000 hours, and 600 hours from Waymo. But then there are some other aspects, the maps. So in Argoverse, we had very simple maps, and also the perception, the labeling of the tracks was rather noisy because it was actually labeled with the online perception system on the car. Similarly, in Lyft, there the maps were better, but again, it was online perception, low quality tracks. So if you go to the homepage, you can see these tracks kind of jumping around, a lot of false positive, false negatives. And obviously that is kind of annoying when you try to train a planner from that. And then Waymo, relatively high quality data set. We'll look at how that is done in a second, but still only for prediction, not for planning. So what we did was to create the first benchmark for machine learning based planning. So machine learning based means it's learned approaches specifically that we're focused on. It comes with a big data set, 1,300 hours of auto-labeled data from 4 cities, but is also, again, a closed loop simulation framework that kind of is initiated by this data set, and then you simulate what happens afterwards. And for people that are interested in end-to-end planning methods, we also provide 120 hours of real-world sensor data. We unfortunately could not include the whole data set because there was something more than 200 terabytes, but this was as much as we could bear financially. So if you're interested in these kind of methods, this might be very interesting to you. End-to-end planning means input is sensor data, output is the trajectory, and then some kind of neural network in the middle. Here is the offline perception that I already talked about. So this is inspired by what Waymo and also Uber did in the past. You can see here a little demo. Maybe not. Yes. This is the data that we labeled from this data set. So this is in Las Vegas, relatively big roads, lots of actors on the road. You can see we have very long range detections, relatively consistent tracks, so not a lot of flickering or challenges like that, apart from the internet connection. So this is very interesting data if you want to train planners or also prediction models from that. And to mention again this offline perception aspect. So the idea is basically that we don't need to run on a car. Therefore, we can take very big models. They can use a lot of GPUs. That is fine. And also they can be a-causal perception models. So we don't just need to look at the past. We can also look at the future and kind of globally optimize the whole sequence. You can do it in the detector. We can do it also in the tracker. And then there can even be another component called track refinement network, which kind of looks at every object track by itself and refines that as well. And then we get very good perception quality. And the Waymo paper was able to show that at least for cars at a low quality threshold, they get human level labeling performance just using this auto labeling method. And we also improved it even further. So then nuPlan is, as I said, a framework where you train your own planner, you simulate the planner, but also the other agents, you measure the performance in different scenarios, and then you compare and visualize your planner versus other planners. And we can do that in open loop, but also in closed loop. Closed loop, of course, means that you're actually simulating the interactions and not just playing back what happened in the original data. And it's nicely modular, so you can plug in different observations, whether it's the sensor data or the boxes, different planners, different agents, different controllers, open loop versus closed loop, and then also different metrics if you're interested. And then we have this large data set in our planners and we evaluate them, and we realize that evaluation on 1,300 hours is relatively, it doesn't tell you a lot if you don't know what happened where, right? So maybe 99% of the time it goes very well, but then a few times it does not. So you need to find out where is it not working well. And for that purpose, we extracted, I think, 71 different scenarios from this data. We mined the whole data set for that. Things like jaywalkers, unprotected turns, etc. Now you have these scenario labels, and now you can go and evaluate your planner exactly on these scenarios. You can see on lane changes, we're doing 5% better with this planner, but on jaywalkers, we're doing worse. So that's nice. Also, traffic lights is something that other data sets had only from kind of computer vision methods, just running them on images to get like green bulbs and red bulbs. What we did was to develop a new method that uses the motion of the agents, so the tracks of the agents, to guess whether the traffic light is green or red. So it's not 100% reliable. You can imagine that if there's a car racing across the red light, our method would say, okay, green. But most of the time, this works relatively well. So let's look at it again. You see here, it's a red light for these actors down there, up there. And then at some point, it will switch to green, and then we will see them starting to drive. Not yet, but very soon. Yeah, now we see them starting to drive. So this is inferred purely from the perception. And the nice thing is it covers all parts of the intersection. So if we want to simulate also the actors on the other side of the intersection, that's also possible with this approach. Okay. So now we had this nice data set, but one thing that we were still annoyed by was that the perception tracks, when you have an object occluded for a while, and then you see it again, then you typically assign it a different track because you don't have this like very long memory. So we developed a new method for, again, auto-labeling offline tracking in this case with object permanence. So the idea is it remembers certain, or it will never throw away track. It will always say the track must be somewhere, and it tries to figure out where that is. Then it just re-ID, classical approach. And then it uses a map prior to figure out how that object behaved between before and after. So you can see that here in the video, there's a bus occluded by a truck, and now it comes back. And we figure out that those two look similar, so it must be the same object. And then we use the map to figure out how it moved between those. And we use motion forecasting methods with a start, but also with an end to kind of fill in the gaps and then nicely completely label the data set. So in conclusion, this second generation of data sets, once developed, it scales nicely, and you can deploy that in new cities, label new data. But the networks are still trained on data that is annotated with human supervision worth millions of dollars. And only big companies obviously can afford this amount of labeling. So that takes me to the third generation, and that's now more of a goal rather than something that is already there. Affordable auto labeling. So ideally, we are able to label data sets much more affordably. So it's again the same loop as before, but this time, let's say we use 1% of the data compared to the existing data set. So perhaps 100 labeled point clouds, and hopefully we can achieve almost the same thing as before, but with much less money involved in human annotation. And why does affordability matter? So first of all, as I already mentioned, we want to generalize, want to scale to new environments, not just San Francisco and Phoenix. Also, we want to democratize AI. So I think it's important that it's also universities and startups and so on that have access to these kind of technologies and data sets. And then the question, how big should it be? That's arbitrary, but I think something like 10 minutes of data labeled, that would be nice because it's relatively simple to collect that and label that. If we get similar performance from that, that would be my goal. So now I look at 3 different ingredients that we can use towards this goal. The first one is unsupervised object discovery and also self-supervised learning. So here's a paper that auto-labels data from roadside units. Roadside units, you can see one here on the side. This is a sensor that's mounted to a traffic light or a similar pole, and it's a LiDAR that scans an intersection, and you can see data from all the cars here. You can actually see some of the tracks over here. And that's relatively interesting because you're kind of looking down at the intersection. You have a pretty good viewpoint there. So what you can then do is you remove the ground plane of that LiDAR data, you cluster the objects, you have some nice clusters. You do some tracking steps to follow them around, so you get kind of a temporal consistency. But then you still have issues because there are a lot of non-moving static objects that you have not detected. So then you use these kind of pseudo labels. You run a self-training step. So basically just train with those labels, you apply it and maybe loop that a few times. And then you have very consistent, nice tracks. And then you throw in just a little bit of labeling, let's say, 1%. And you get relatively good performance. And we did this here on 2 data sets. So with 1% of the labels on this data set and 5% down here, we get performance that is relatively close to the fully supervised baseline. So within 2% or so, using very few labels. And the reason why this worked so well in this case is because of this elevated viewpoint of these roadside units. So if you're in an autonomous vehicle and you're looking at another car, you typically just see 2 sides, But if you're a bit higher up, you see kind of the four sides to some extent, or at least where the roof ends. And that's very useful to label this data reliably. So this is a very affordable approach of auto-labeling data. It just requires that you install a lot of roadside units. And another paper is about scene flow estimation. So scene flow means every LiDAR point, how is it kind of translated to the next point cloud? What was the motion between those two? And what we use here is actually iterative closest point. Again, on object clusters. So it's not the entire point cloud, but we remove the ground cluster, and then we do ICP between different clusters, and we use it as a kind of matching technique. So very old approach in some sense with some tricks there. And that alone gave us already state-of-the-art scene flow performance versus all the deep learning techniques. But the method is still relatively slow. So it's 3 seconds runtime. That's obviously too slow to run on a car. So next, we also took one of the state-of-the-art methods that is very fast, and we used our data as labels for that. And then we get a method that is very fast as the fastest existing method, and also still pretty decent on the performance. So that is interesting because some of these methods are actually, or many of these methods are actually using labels for scene flow. So they're kind of using the object bounding boxes. We get state-of-the-art performance without any labels involved. Okay, ingredient number 2 is called active learning. It's also a very old thing. So the idea in active learning is that you use a machine learning model to decide which data you should be labeling, rather than a human sitting down and saying, oh, this clip here looks interesting, let's label this, which is what we did in the past. The machine now decides what should be labeled. This was a recent paper, I was actually here at ICRA, where we looked at how active learning methods typically work. And typically how they work is they sample 1% of the data set randomly, they let a human label that, and then afterwards they have a detector trained on that, which can kind of improve the performance further. And we said, why do we start with random labeling? Let's start with a smart initialization. And our observation was basically that you want objects of all sizes. So you just kind of, again, removing the ground here on the left side, you clustering objects, and then you get small clusters, medium clusters, and large clusters, and they happen to look a lot like pedestrians, cars, and buildings. And then you're kind of sampling uniformly from these clusters and also the ground. You're throwing that in for the active learning loop as your initialization. And then you start out already 7-8% better than all of the existing methods. And then also in the end, your performance will be much better. So here with 5% of the labeling effort, we got performance that was on par with the full data set. So it's about 20 times more data efficient than standard approaches. And the last one is obviously, I cannot present anything today without foundation models or language models. So that's also an important thing. This paper is still, we're still work in progress. I cannot show too many details, but it's based on the idea of Dino. Dino V2 is, of course, a famous paper. And these appearance embeddings are very interesting for us because if you look at these elephants here on the left side, even though one is a real elephant, the other is a kind of statue, the embeddings, if you look at the front, the nose part, is very similar. Similarly here, this bird versus aeroplane, if you embed them in a low dimensional space and color it accordingly, the wings and the head part between those two are very similar. So that's interesting as an unsupervised method for kind of retrieving objects that have similarity. And speaking about language models, so in this work, it's not about autonomous driving, but here the goal is to figure out all the objects in a scene and then their relations as well. So here we have an example of a person cleaning a motorcycle, and the relation there is cleaning. And we use first kind of classical methods to get the person and the motorcycle, but then the question is, what is the relation? And here we ask GPT or Llama about that. Is this relation person cleaning motorcycle likely? And it will tell us, yes, it is likely. And also a person uses brushes, a hose, cloths, etc. So various tools. So the network tells, the LLM tells us, first of all, if it's likely, and second, what it looks like. We can embed this text and the visual in a similar space and then improve our performance significantly over the state of the art here. And in the follow-up work, we do something very similar. Also, again, with large language models or multimodal large language models. But in this case, it is open set. So now some of these relations between these objects, like flying and observing, they are known. We've seen them in the training set. And then other relations are not known. They're close. So that's the other way around. So some relations are not known, and those we learn from the large language model. So we kind of use their embedding of the concept of playing, which will tell us it's similar to fighting. And that gives pretty good performance again, only about 10% worse than the fully supervised cases. Okay, so in conclusion, the third generation of these data sets and the methods that work on them, the goal is to have affordable auto-labeling methods, and we use techniques like unsupervised object discovery, self-supervised learning, active learning, and also, of course, foundation models and large language models. And the future work will need to learn how to combine these different approaches, because now there's a bunch of separate papers, but we really want to have one system that can do these things jointly. And the goal is to drastically reduce cost, democratize AI, and also create some new robotics applications. So I have some examples here: trains, bikes, and boats. And this is actually something I'm working on at the moment. So we have a pretty nice bike with 3 lidars, 3 cameras, etc. And we're going to build a nice data set from that as well. Here's just a first teaser, if the internet supports it. Okay, here's just see some a brave student cycling around on a bike with lidar equipped. So that's also going to be very nice data in the future. If you're interested, for example, in motion forecasting or planning for bicycles via use, you might be able to use this data. Yeah, or not. And just very briefly, this is a upcoming work still under review called NeuroNCAP. That might be interesting to some of you here. What it is essentially we're using nerves to render scenes that are based on real scenes in nuScenes, but then we modify the actors in there. So again here, real world data set. Now we are taking these scenes and we're editing the actors. And we are creating 3 different scenarios. So the scenarios are stationary actors. You can see it here. The car stopped in the middle of the road. But also, of course, at 360 degrees. And another scenario is frontal. You see that here on the left side, a frontal collision, and on the right side, we have a side collision. So car racing towards us from the side. And in all of 3 scenarios, if we don't do anything, we will crash. So the question is, how does a planner need to react? And we are using UniAD and VAD, so kind of the state-of-the-art end-to-end planning methods for that. And we're just running that on a lot of scenarios and just figuring out where it crashes. And the results are pretty shocking, because in the majority of the examples, the state-of-the-art in end-to-end planning crashes. And this is, of course, because they are trained with public data sets, and public data sets don't have crashes by definition, because no company would ever release data of a crash. So the question is, how can we get around that in the future? We don't have the answer, but we have a nice benchmark tool for you to evaluate your planners and hopefully build planners that are more robust. Here you see again, crashing. So I hope that will be some inspiration for you in the future. Okay, so yeah, I think we've seen all of this. Thank you very much. And if you have any questions, you can.
Great job, Holger. So we have time for some questions for Holger. So a lot of cities have traffic light cameras on top of their traffic lights. Is it possible? So, sorry, first of all, thank you for the great talk. A lot of cities have traffic light cameras. Is it possible to do any of this auto labeling with them, or do you need like much nicer sensors than that?
So I do think kind of recent generation of traffic light cameras should be good enough. Of course, in this example, it was LiDAR, but I think that's we can definitely also work with cameras. I do think the big elephant in the room is privacy. So in some countries that may be more possible to get that data than in other countries. I think that is the biggest challenge. And then also, of course, you really do need a lot of those traffic cameras. So if I, as an academic, now put up 10 cameras somewhere in town, that's not going to help anybody. But there are some data sets, and they are brave for doing that, but it does not generalize again. So we do need really a lot of those cameras. But I do think it's an interesting approach in countries and cities that are already having that infrastructure. And I think the quality is not such a big concern. In fact, the main thing that you get from that is probably not the perception, because it looks very different if you look from downwards, but rather the trajectory information, right? And that is kind of independent of the exact sensor.
Thank you. Thanks for the great talk.
Thank you.
Hi, thanks for the great talk. My question would be, do you have any ideas except for the map-based auto-labeling to extend the range? Because we have the issue that for unprotected labs, we need much more than the 100-meter range that is currently available.
Yeah, how was it related to map-based?
You presented the map-based approach. If you have map knowledge, you can have
okay,
few points only to track your object, but that requires a map, of course.
Yes, this is. Yeah. So, I mean, first of all, of course, we need better sensors, right? Some of these data sets, like the nuScenes was a 32 beam LiDAR, is getting a little bit old. So that's the first thing. Radar, especially, of course, is very nice for very long range. So we're doing a lot of work on that as well. But yeah, it is a problem. The maps in general are a problem, right? We do want to get away from them, at least the very high definition maps. So maybe we can use something really low definition, OpenStreetMap or something like that. It is still a big challenge. So I think you do need to have some price for that particular work, the offline tracking of object permanence. So without any price, I think it's going to be quite difficult to do that. We can talk more. Thank you.
Hi, very interesting, very thorough work covering all aspects of driving. Kind of philosophical plus technical question. Given that the auto labeling will always have some accuracy error, how much accuracy is needed to say that downstream everything is going to be accurate enough? Right?
Yeah, it's a good question. I think it's really a question also of long tail problem. So I think for cars, it's good enough already. So I think we're done with cars. I think it's really about the rare classes. So already bicycles is already a problem. And then if you think of something really rare, I was just traveling a bit in Asia. I saw some interesting vehicles that none of these data sets would be, or methods would be able to detect. So I think it's mostly a question of that, like how rare are these classes, whether we are able to auto-label them or not.
I was not thinking necessarily about things you have not seen, at least on a regular basis, but rather the errors for the classes you have trained enough. Let's say you get 99.999% accuracy. Is this good enough, or is it going to be good enough? Because even if you have, let's say, over millions of data that you're going to be training, these are going to be frequent enough that can potentially cause errors downstream that you cannot easily detect. And I'm wondering if empirically, or at least theoretically, there is a threshold that you are going to say 10 in the minus 12 is going to be the accuracy I'm going to expect, so that after that, I don't care, because all the other learning and stuff is going to ignore any of the mistakes that are happening in it.
Yeah, so I think in the first step, we're just trying to be as good as the human. But of course, the human is actually pretty bad annotator themselves, right? They make a lot of mistakes too.
May I object to that? Humans are excellent. The annotation process is bad, right? Because I don't think anybody has evaluated perception systems of humans driving and say, oh, you made a mistake. You didn't see the bicycle there. You thought it was a truck or an elephant, right?
Yes. So it's the distracted human annotator that is flawed and the tools around it and everything. So I do think that's a big challenge. In my experience, though, some amount of annotation error can be dealt with. So I think the network just kind of, if 10 times you annotate it and one time you don't, it will learn that concept. I have done some studies on that in the past where we really try to insert more and more noise. And I think the methods are pretty robust to that. So even, 1 to 3% of labeling errors, depending on how you define them, is typically fine. So I think that's not the biggest challenge. The bigger challenge is if you're missing the 100% of the ambulances or something like that. Thank you.
Okay, very nice presentation. I'm Maciej, I'm a PhD student from KTH. I'm also working a little bit on supervised learning for autonomous driving. And my question was like you were presenting a lot of different ways to learn and to create the data and to label data, but maybe something which was missing for me was how these models translate between different vehicles, right? So of course we can create a lot of data, for example, on nuScenes, we can create similar data on nuScenes or through like NeuroRapt from Zensack, right? We can of course create a lot of new scenarios, but it's still, or at least I feel that it's still kind of, it's still gonna work, but it's gonna work on the same domain. And what are your thoughts how we can translate it, let's say, between different domains, between, let's say, new cars?
Yeah, so I think it depends again on which task and so on. I guess you're mostly interested in the planning part, or?
For me, it's more object detection.
Okay. So I think the good thing is in perception, especially camera-based, is relatively robust. So I think we're getting these foundation models now for, you know, like segment anything. It really works pretty well. Or some people disagree, but I was impressed. So I think camera is relatively robust, but then when we're looking at LiDAR, it's already bad. We don't have real foundation models for LiDAR. When we look at radar, it's much more messy, right? Depending on the wavelength. So I think that is much more challenging to build a model that can work for everything there. So that's still, yeah, work in progress, I think.